So if you've got a sine of some unknown angle and it's equal to 1/2, you're basically asking, all right, sine that's my y coordinate, where's the y coordinate equal to 1/2? So where it's like something, comma, 1/2. That's what we're looking for. Because if that angle has a y coordinate of 1/2, then I know that the sine of that angle is 1/2. So let's take a peek at that unit circle. And so just kind of start looking and think, y coordinate is positive 1/2. Where are the positive y coordinates? Which quadrant should I be looking in for positive y coordinate? 1, 2, 3, or 4? Yeah, isn't positive y going to be just up? So it's going to be somewhere in quadrant 1 and quadrant 2. That's where the positive y coordinates are, because you're moving up from like the origin, right? If you think of this is still a coordinate plane with a y-axis and an x-axis. And so we know that y is always positive when you move upwards. And so I'm only looking in those upper halves, the quadrants 1 and 2. So looking for the y coordinate. And just starting off at like 30 degrees, check it out. Right there I see, oh, this angle has a y coordinate of 1/2. What's that angle? Oh, it's 30 degrees. Or pi over 6 if we're talking radians. So I know that if I were to say, or type in my calculator like, hey, the sine of 30 degrees, what's that equal? Well, the sine of 30 degrees would be that y coordinate. It would be 1/2, which tells you that my answer to that original problem is 30 degrees. So going back, which angle has a sine of 1/2? Well, 30 degrees is one of them. Or if you want to think of that in radians, pi over 6. And there's another one. What other angle did you find has a y coordinate of 1/2? Right over there, right? 150 degrees. Also has a positive 1/2 for that y coordinate. And so I know at these angles, same angle, just different units, would also have a sine equal to 1/2. So you can say at 30 degrees or at 150 degrees, which is the same as 5 pi over 6. So those are the two angles with it. Are those the only angles with a sine equal to 1/2, do you think? 30 and 150? Are there any others on this circle that we can use? What about any angles that aren't on this unit circle that we could use? Ooh. What am I talking about? Are there angles other than the numbers from 0 to 360 degrees? Can you go bigger than 360? Yeah, so imagine if I was at 360 and I went up another 30 degrees, what angle would I be at? That'd be 390, wouldn't it? 390 degrees. These are essentially the same angle, right? 30 degrees and 390 degrees. Do you remember what we call angles like that? They have a special word. Starts with co. Terminal. Yeah, coterminal angles. Anyone remember the word coterminal angles? It's okay. It's all right. Do you remember hearing that maybe? No, all right. Those are called coterminal angles. So where you spin around a whole 360 and you're at the same angle still, it's still going to have the same values. So I could even add another 360 and get up to 750, and that would also have a sine of 1/2. You can add another 360. So there actually are an infinite number of angles with the sine equal to 1/2. But for now, I just want you to recognize it's just on the single unit circle. All right. How about the other one? Did anyone find any angles? Let's just do some degrees first. Which angles have a cosine of negative root 3 over 2? What'd you find? 150 also? That was over there for sine. 150 degrees. Anybody else agree? 150 works? All right. Someone else? What other angle has a cosine of negative root 3 over 2? 210? Anybody else get 210? Yeah. And 210 degrees. So let's look at those two angles on our unit circle. 150 and 210. So those 150, that's right here. And since this is cosine, I'm actually looking at the x-coordinate, right? Because cosine is your x-coordinate. And so this angle has a cosine or an x-coordinate of negative root 3 over 2. In which other angle, 210, because check it out, that also has a negative x-coordinate, a negative root 3 over 2. And notice that this is now quadrants 2 and quadrants 3, because cosine is negative to the left, right? Your x-coordinate is always going to be negative to the left in quadrants 2 and 3. And so you just look at those coordinates and say, oh, well, cosine of those angles would be negative root 3 over 2. All right, that's our whole goal for today. We're solving trig equations. So in essence, that's what these are, these original problems. This right here, it's an equation, right? Because there's an equal sign, it's an equation. And there's an unknown variable that we're solving for. We're solving for x. We're going to do that by looking at the unit circle. You see that trig function, you see what it equals to, and you're kind of using our knowledge of how those coordinates relate to the angles on the unit circle to identify this, to solve that equation essentially. We know that these are the answers. Both of these answers I could plug in for theta there, and that would work. That'd give me that correct answer of negative root 3 over 2. That's the solution to an equation. They're the values that make that equation true, the left side equal to the right side. Whoa, whoa, whoa. So this is it for trigonometry. 9.6C. This is our last learning target for trig. 9.6. We've been working on this one kind of throughout the week, actually. This is our end goal. This is why I had you work on those trig identities, those relationships throughout the week, because we're going to be using them to help solve some of these trig equations. And to solve a trig equation, just like I just mentioned with that warm-up, you're just finding out, hey, which angles make the equation true? Just like any equation that we've solved throughout the year. You know, when you're solving for x or y or whatever, you know that you've got the solution when you have a number, an answer, that if you were to plug that number like back into the original problem, it would make it true. It would make the left side equal the right side. That's how we know we have the solution. Sometimes we'd have extraneous solutions. Ooh, don't worry, we're not going to have those for this. I know you hate those, right? Some of you are like, what's extraneous mean? Never heard of that before. Oof. And now I do want you to note that, hey, most of these equations will have 2 solutions. Some might have more than 2 even. Crazy. But some will only have 1. And we'll look at some of those. And so you already kind of did this right here. You don't need to draw that unit circle or whatever. This is just kind of going over that warm-up. And so when I ask you, like, hey, which angle has a y-coordinate of 1/2? That's how you should be thinking about these trig equations. It's kind of how I phrase that warm-up for you. You know, sine of x equals 1/2. That's really saying which angle has a y-coordinate of 1/2. Because the y-coordinate is the sine ratio. So that's what we're doing here. Let's break it down. There's really 2 steps for solving these equations. All right, nice and simple. The first thing you want to do is isolate a single trig function. This is the same step that you do for like any equation. You know when you like cancel stuff out, you move things over to the other side by like adding or subtracting it or dividing or whatever until you get like x by itself. Same idea. But we're trying to get just the trig function by itself. So if you want to make a note, this is just like your basic algebra. Where you're like canceling stuff out. All right, so first thing, just think basic algebra. Get the sine or the secant all by itself on one side of the equal sign. That's your first goal. Because you might have like sine of x plus 1 equals 0. Well, your first step would be to get rid of that 1, move it to the other side so I only have the sine of x on one side of that equal sign. Right? That's your first thing that you want to do, your first focus, your first goal. Ultimately, you want to simplify that equation or change it or cancel stuff out until it looks something like this. So that on one side I have just a single trig function, like sine of some angle, whether it's x or y or theta or whatever. You have a single trig function. And on the right side, you got some number, some value that hopefully should look like one of those coordinates on our unit circle that we know and love so well. Because once your equation looks like this, then it's time for step 2, which is what you did in our warm-up basically. You look at your unit circle and you try to figure out, all right, which angle has that value? So which angle has a, when I say value, I mean look at first your trig function, sine, and think, all right, which part of the coordinate is the sine asking for? And we know that, oh, sine, that's the y coordinate. So you're looking for, where's there a y coordinate? Of the square root of 3 over 2. And that's it. So that's how you're going to solve these. So you look at that unit circle. And like, all right, sine y coordinate, root 3 over 2. So it's positive, so I'm thinking upwards for y coordinates. Y coordinate, boom. There's a positive root 3 over 2. There's another root 3 over 2, both positive. So my answers are there and there, whether I'm doing degrees or radians. So that'd be the solution to that. Sine of x equals root 3 over 2. That'd be both of those angles. One thing I do want you to be aware of, I kind of mentioned this earlier, how there's like an infinite number of solutions if I keep on spinning around the unit circle from these coterminal angles. Again, you don't need to write this all down. This is just for your own knowledge. Oftentimes, I'm only looking for just that one angle on the unit circle. So sometimes when you solve problems, like on Delta Math, for example, and in later courses in pre-calc and calc and stuff, you'll see the question asking, hey, solve this equation, and then you'll have something like this written, for 0 is less than or equal to x is less than 360. All that's saying is solve it for x so that it's in between 0 and 360. Basically saying just find that one angle or the two angles on the unit circle. You know, don't worry about coterminal angles at like 720 or 1080 or whatever like that. Same thing with radians. So if you see here between 0 and 2 pi, again, that's just a single rotation on the unit circle. It's saying just find the angles on the unit circle that you know and love. Don't worry about those additional spins on the circle or coterminal angles. You okay with that? So if you see this, that's all it's saying. It's saying, hey, just solve for x is in between these two numbers. All right, go ahead and try some of these. We've got 2 examples on the board. 5 equals 6 plus the tangent of x. I'll do this first one with you. For your answer, the left column that's asking for degrees, the right column would be asking for radians because it's got pi in it. So let's do this top one together. So make sure you've got that written down. 5 equals 6 plus tangent of x. Now remember I said there are 2 steps for solving these equations. First thing we want to do is try to isolate or get by itself the trig function. Well, what's my trig function in this first example? Tangent. Is the tangent all by itself on one side of the equal sign right now? No. What else is on that side with the tangent? Got to get rid of that 6, right? How can I get rid of that 6 that's on the right side? What would we do if it was just a basic algebra problem? Just subtract it, right? That's a positive 6. So let's start by doing that. We're going to subtract 6 from both sides, so that cancels out. What's 5 minus 6? So negative 1 equals the tangent of x. Is that trig function by itself now? Tangent? It is. It's all on its own. That's great. That's what I wanted. The trig function is by itself. So now I need to solve this. So that's where our unit circle is going to come in handy. I want to know where tangent is equal to negative 1. Let me go dual screen here for a moment. Whoa. No, undo that. Go left. Get rid of this. Okay, that's what I wanted. There we go. All right, so I'm going to look at my unit circle here. I'll make this a little bigger for everybody. And I want to know where tangent is equal to -1. Now, tangents, we got to think a little bit more. Since tangent is, just make a little note, that's the y coordinate divided by the x coordinate, right? Tangent is like opposite over adjacent, the y over the x. So this is one of the trig functions where you need to look at both coordinates, the x and the y. Now just do a little thinking here. If I'm dividing two numbers, like a y coordinate and an x coordinate, and I get a 1, what has to be true about both that x and that y coordinate? If you divide two numbers and you get a 1, what has to be true about those two numbers? If they were different numbers, would we get a 1 when dividing them? No. Only if you divide a number by itself do you get a 1. They like cancel out. Are there any angles on the unit circle that have the same x coordinate and the same y coordinate? Yeah, what are those coordinates? What would they be? How about right there at the 45 degrees? Root 2 over 2 and root 2 over 2. If I divide those by each other, what would I get? 1. Yeah. So the tangent of that angle would be 1. Oh, but wait a second. This is asking for a tangent of -1. All right, so if I divide two numbers and I get a -1, they still need to be like the same quantity, the same number, but what has to be true about just one of those values, either the x or the y? One's got to be negative. So which angle should I look at? Awesome. So I know in quadrants 2 and down in quadrant 4, that's where I have a positive x and a negative y, or a negative x and a positive y. I have one of each. So the angles that we'd be looking for are these. A negative root 2 over 2, root 2 over 2, or this angle here, root 2 over 2, and a negative root 2 over 2. If I took either of those y values and divided them by the x value, I'd get a -1. So that would be our angles that we're looking for here. So where's the tangent of x equal to -1? Going back to our slide on the right here. It's not this, but we see that angle and this angle. So in degrees, we have two answers, right? 135 degrees or 315 degrees. And on the right column, I have 2 pi here. That's just me asking, hey, can you find the answer in radians? Same angles, right? You just look at the radian number. That's 3 pi over 4. And in quadrant 4, that'd be 7 pi over 4. I'd like you all to try to do the same thing with that second example. Let me make that a little bigger for you. All right, 2 cosine theta equals -3. Try that one on your own. See what you can figure out. Again, it should be getting 2 answers. And I want you to write them in both degrees and radians for now. So get the cosine by itself first. Yeah, awesome. Yes, great. So its cosine, is that the x coordinate or the y coordinate? Yeah, good guess. You got it. You knew that. And so then you're looking for where's there an x-coordinate of that number. So look at all your coordinates. Where do you have an x-coordinate equal to that? Yes. Yeah? Nice. Good? Awesome. Awesome. You okay with this? Nice. Okay. Yeah. So it's a negative root 3 over 2. Cosine is is that x or y? So close, try again. Yeah. So you're just looking for x coordinates of that. There should be 2 of them. Got it? Got it? Yep. So cosine is your x coordinate. So where's there an x coordinate of that? Yep. And there's one other. That's right. And so you would just write those 2 angles. That's your answer. That's it, man. All right. I love what I'm seeing. You're catching on. This is great. So first thing, we need to get that cosine all by itself by dividing by the 2 in front, right? That coefficient, that means it's being multiplied. The opposite would be dividing by 2. So we divide both sides by 2. Those cancel. And ultimately, we're saying, hey, the cosine of some angle theta equals negative root 3 over 2. So we're looking for an angle whose cosine, or x-coordinate, is negative root 3 over 2. And so looking at our unit circle over here, it's cosine, that's the x-coordinate, so I know I'm looking in quadrants 2 and 3, because that's where x is negative to the left. And a negative root 3 over 2, I see one there, see one there. And so then my answers, my solutions, let me slide this down a little bit. In degrees, we've got 150 degrees or 210 degrees, and then the equivalent radians would be 5 pi over 6 and 7 pi over 6. Anybody have those values, just out of curiosity? Oh, terrific, terrific. That's really good. The unit circle's handy, isn't it? Isn't it good that you learned it so well? You thought it wouldn't be useful. And don't you dare say, but outside of math class, what am I getting? No, it is useful, trust me. You're smarter for it. Getting smarter every day. Let's see. Hey. All right. Sometimes we're solving the equation. We're going to have an exponent in there. Boo, exponents. Tricky. Oh, wait, hang on. There we go. So let's solve this together using basic algebra. So just write this down. I'm going to walk through this one with you. It's got one little difference in it that we need to be cognizant of. So 2 times the cosine squared of theta minus 1 equals 0. So get that written down. 2 cosine squared of theta minus 1 equals 0. Whoa, that's jumbo. All right, let's do some basic algebra. I want to get the cosine all by itself on what side? What should I cancel out first? Whatever is being added or subtracted, there's a minus 1, so I'm going to add 1 to both sides. This becomes 2 cosine squared of theta equals positive 1. All right, so you get rid of what's being added or subtracted. Next, you get rid of anything that's being multiplied or divided. This cosine squared is being multiplied by 2. To cancel it out, you would divide. by 2. So those are gone. And now we have the cosine squared. Well, that's ugly. Cosine squared of theta equals 1/2. And hey, look at that. I've got the trig function all by itself, right? There's nothing else there. Oh, wait a minute. There is one other thing there. I don't just have the cosine of theta, which is what we need. There's that exponent, that square. We need to cancel out that too. Any ideas? How do you cancel out something that's being squared? Isn't the opposite of squaring square rooting? Can we do that? So like the square root of cosine squared, would that just be cosine? That's how that works, right? Like the square root and the square, they cancel each other out. Yes, that's valid. But yeah, if I canceled out one side, or square root one side, I've got to square root the other side. Oh dear. So this equals the square root of 1/2. Now, square root of a fraction can be a bit daunting at first, but if you recall our basic properties from our rational functions or radical functions from earlier in the year, we know that if you take the square root of a fraction, that's the same as, here, I'll just work with that. The square root of 1/2, that's the same thing as the square root of 1 over the square root of 2. It's like you just take the square root of the numerator and denominator separately in the numerator and then in the denominator, and you can simplify each of them on their own, and it's the same thing. Well, that's kind of nice because what's the square root of 1? 1 squared is just 1, so that's nice and easy. Unfortunately, I can't simplify the square root of 2. That's not a perfect square. And if I look at that fraction, I have 1 over the square root of 2. Do we like having square roots in the denominators? Nope. How do I get rid of that square root of 2 that's in the denominator? So we can just rationalize that denominator. If we multiply by that root, which is pretty simple, times root 2 over root 2, this is going to change. In the numerator, I'm going to have the square root of 2, right? Because 1 times root 2 is just root 2. In the denominator, square root of 2 times the square root of 2 is just the 2, right? The radicals cancel out and leave you with just that radicand. So going back to our problem, this is actually that cosine of theta, root 2 over 2. Ooh, one thing I forgot to do, though. Even put a note up here to remind me. Remember, when you take a square root, you actually get 2 answers, a positive and a negative. That's because, like, if I said x squared equals 4, well, x could be 2, or x could be a negative 2, because both of those numbers, when you square it, equal a positive 4. So I have to take both those into account. So right here, I took this square root on both sides. I technically had to put that plus and minus in front of it. So the cosine of theta equals either a positive root 2 over 2 or a negative root 2 over 2. Can be both of those. So now, unit circle time. Look at your unit circle, and you're trying to find which angles have a cosine, or an x-coordinate, of a positive root 2 over 2 or a negative root 2 over 2. So look at your unit circle, write down which angles have a cosine of root 2 over 2 or negative root 2 over 2. Nice. Hey, how many did you find? 4. Holy moly. 4 of them. Yes. So cosine, that's my x-coordinate. So going around the circle, I know the root 2's are only at all the 45-degree angles. So I see a positive root 2 over 2 or negative root 2 over 2. I have to look at both of those. Down there's another negative root 2 over 2, and here's another positive root 2 over 2. So there are 4 different angles that work. Now, I didn't specify degrees or radians for this one, so pick either one, that's fine. And so our solution for this would be 135 degrees or 45 degrees. What else? 225. Whoops. And 315. Or pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Any questions yet? So when you see a squared in there, remember that you're going to get multiple answers. You have to remember that plus and minus. But you know, it doesn't happen too often, but we do need to be aware of it. All right, let's see if you can try one on your own. Dun, 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 dun. Example 2. 4 times the sine squared of theta equals 3. If you can't see, this just says example 2. I'll make that bigger for you. All right, try this on your own. Solve that for sine. Just get that sine by itself. Yes, good. You can just use degrees by default if I don't specify. I'm fine with either. On a test, I will say, hey, solve this in radians or solve this in degrees. So can I take the square root of either of those values? Right. And so now that's your equation, right? Sine equals this. That's when you're going to look at the unit circle now and try to find what angles would that be true for. Remember, take the square root of the numerator and the denominator separately. That square root of that denominator. What's that equal to? The denominator. What number is this? Calculate that. The square root of that.
Oh, 32.
Yeah. This first one's good, but it's a positive, and sine is positive in this quadrant and this quadrant, 1 and 2. So it wouldn't be the 330, because down here that's a negative. See how that's negative? You're looking for the positive. All right, love, love, love what I'm seeing. We divided by 4. Sine squared is 3 over 4. Since it's squared, we got a square root. So that the square root and the square cancel out. And so we're looking for the sine of theta equals, now this little mini problem here, the square root of 3 over 4, that's square root of 3 over the square root of 4. And hopefully you recognize that the square root of 4 is just 2, right? So now you're looking for the sine of theta equals the square root of 3 over 2. Except for one other thing. Did you all remember plus and minus? Oh. Oh, all right. Some of you did. So we're actually looking for every angle with a y coordinate, since it's sine, that's the y coordinate, of a positive root 3 over 2 or a negative root 3 over 2. So how many answers are you going to get, everyone? 4 of them, right? You're going to have one of those in every quadrant. So going back to the left here. All right, sine, that's the y coordinate. And so what do we got? Root 3 over 2, root 3 over 2, negative root 3 over 2, negative root 3 over 2. So I've got 4 different angles with a positive or a negative square root of 3 over 2. All of them are valid. So we've got 60, 120, 240, and 300. Woo! I don't know how to scroll. Or if you did radians, pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So 60, 120, 240, and 300. Anybody have all 4 of those? All right. That's wonderful. Really good work, everybody. Nice. The fact that you're getting this is kind of like we've been spending a month building up to this, and you're getting it. Oh, it's fantastic. Good job. Reciprocal trig functions. Woo! Secant, cosecant, and cotangent. These are reciprocal trig functions, which we know about them, right? We've learned about them. But solving for them can be a little trickier because it's not like secant is just the x coordinate on the unit circle or just the y coordinate. So for these ones, you just have to think upside down a little bit. Since these are reciprocal trig functions, we look for their reciprocal on the unit circle. So let's solve this one together first. Secant of x, or root 3 times the secant of x equals 2. What do I have to do to both sides to solve for secant? Do what? Yeah, just division, right? This is being multiplied. To cancel it out, we would just divide. All right, so divide by root 3, divide by root 3, cancel, cancel. And we see that, hey, the secant of x equals 2 over the square root of 3. Now, don't rationalize that denominator yet. I know you all are like, oh, I got to get rid of that root 3 in the denominator. Okay, maybe 2 of you are actually thinking that. The rest of you are like, isn't that okay? So since this is a reciprocal function, it's okay to have a root in the denominator. I still need to find this somewhere on the unit circle. But secant, I don't know, is that x, is that y, is that x over y, y over x, something like that? Here's what you want to do. Once you get a reciprocal trig function by itself, just like I have here, right? Secant of x, nothing else on the left side. What you're going to do is take the reciprocal of it. What's the reciprocal of secant? Cosine, right? 1 over cosine, basically. So watch this. This is pretty cool. Secant, that's the same thing as 1 over the cosine, right? So 1 over the cosine is 2 over root 3. Aren't those, that's the same thing, right? Secant is 2 over root 3, so 1 over cosine is 2 over root 3. So I'm actually looking for 1 over cosine equal to 2 over root 3. Well, that kind of looks weird, but here's what's really fun. If you have one fraction equal to another fraction, if you flip both sides, it's still going to be equivalent. So take that left side, 1 over cosine of x, and I'm going to flip it upside down and say, oh, that's the same as cosine of x over 1. So I'm flipping the left fraction. I'm allowed to do that if I flip the right fraction also. That was 2 over root 3. If I flip it, it becomes root 3 over 2. Now dividing by 1 doesn't change anything. So in essence, I'm looking for this. Where's the cosine equal to root 3 over 2? So with reciprocals, if you take the reciprocal of one side of a fraction, you have to take the reciprocal of the other side of that fraction, and it's still equivalent. So we have to remember what these reciprocal trig functions are. So now from here, this is the problem that I'm trying to solve. Cosine, it's an x-coordinate. Go back to our unit circle. Where's there an x-coordinate of root 3 over 2? What'd you say? 1 and 4. Yeah, on the right side, so quadrant 1, quadrant 4. Let's see, root 3 over 2, cosine, that's the x-coordinate. So boom, right there. Right there. So we're looking at a 30 and a 330. So we can say, hey, x equals 30 degrees and 330 degrees. So just be careful with those reciprocal trig functions. Do you want to try one of those reciprocal ones on your own now? Wouldn't that be fun? Yes, Mr. Wojcik. Okay, cool. Glad you're excited. All right, so you can do it this. Square root of 3 times the cotangent of theta plus 5 equals 6. Solve the equation for theta. This one you have to think a little bit more about what happens when you divide two fractions. Just a root 3, right? Like, yeah. What is it? Tangent is which coordinate divided by which coordinate, though? So anytime you have any number, like if I had the number 5, to make it still 5, I'd always divide it by 1. Because like 5 divided by 1 is still 5. So if you have just a trig function by itself, essentially it's already in the numerator over 1. It just helps you think of it. So now, what's the reciprocal of cotangent? Is it sine, cosine, or tangent? Yep. So let's rewrite this now. I'm going to flip this and basically say, well, that's the same as tangent of, and then flip that as well. So take the reciprocal of both sides, basically. Yep, still theta, it's the same angle, but then it equals the reciprocal of this. Yeah, good. So you're looking for this combination. Now remember, tangent is y divided by x. Yeah. So you need that x coordinate, that y coordinate. All right, so I'm going to subtract 5 and get 1. Then I'm going to divide by root 3 on both sides. And we get to the point where we've got, hey, the cotangent of theta equals 1 divided by the square root of 3. Cotangent is a reciprocal trig function. So I want to take the reciprocal of cotangent. What's the reciprocal of cotangent? What trig function would that be? Tangent, right? They both have the word tangent in them. Cotangent and tangent. They both have tangents. So I'm going to take the reciprocal of cotangent, which is just tangent, and I'm going to take the reciprocal of the right side. Well, the reciprocal of 1 over root 3 would be root 3 over 1. I'm just flipping both sides. So I'm looking for which angles have a tangent equal to the square root of 3. And that's a little bit tricky because if we remember, tangent equals y divided by x. So I need to find a pair of numbers, an x and a y coordinate, that when I divide them, it simplifies to become just a square root of 3. Now, first off, how am I going to figure this out? I'm looking at this square root of 3, and I'm thinking, okay, only some angles have a square root of 3. Okay, if I look at this unit circle, so like there's root 3, these have a root 3. Like in each quadrant, there's just that pairing. We have a root 3 over 2 and a 1/2, or a 1/2 and a root 3 over 2. I know that it's not going to be one of these angles because that doesn't have a square root of 3 in it. That can't happen. I know it's not going to be one of these angles either because that's just a 1 and a 0. That's not going to be it. So I know it's got to be one of those two angles. So you need to think about, all right, if I divided the y coordinate by the x coordinate, so either root 3 over 2 over 1/2 or 1/2 over root 3 over 2, which way that if I divided those, would I be left with just a square root of 3? Essentially, the 2's would cancel out. And if I take this angle right here, take the y coordinate and divide it by the x coordinate, the square root of 3 over 2 over 1/2. If you were to divide those, well, look what happens. Dividing by a fraction is the same as multiplying by the reciprocal, right? Instead of 1 over 2, I'm multiplying by 2 over 1. Hey, what happens to those 2's, everybody? 2 on top, 2 on the bottom. This leaves me with just a square root of 3 over 1. Yeah, that's the one you had to think of, tangent. You have to do a little bit of work. We see that we get a tangent of root 3 right there at 60 degrees. Now I need another angle where that happens. Did anyone find the second angle? Which quadrant should I look in first of all? 3. Because it's a positive, and I'm taking two numbers and dividing them, I'm getting a positive. So that can happen if it's a positive x, positive y, or if it's a negative x and a negative y, because two negatives cancel out. So I'm going to look down here in quadrant 3. I want those in the same order, with the root 3 over 2 as the y coordinate, and then the 1/2 as the x coordinate. So my other answer would be right there, 240. So my solution, theta equals 60 degrees and 240 degrees. That's as complicated as it's going to really get in terms of identifying the angle on the unit circle. And by complicated, we're dividing two fractions, which if you really step back and think about it, that's something that you've done years ago. Questions on this? That was a weird one, I know. A few extra steps. One last thing. Remember those amazing trig identities that we've been learning all week long? Here's where they come into play. If I look at this right here, sine squared times cotangent times cosecant equals negative root 2 over 2. Which angle, that if I plug in for x, now that means this x, and this x all have to be the exact same angle. What is that angle that if I took the sine squared of it times the cotangent of that same angle times the cosecant of the angle would result in negative root 2 over 2? That'd be impossible for you to think of and try. I mean, you'd have to test every single angle, multiply them all together, and see, is that negative root 2 over 2? No, try again. That's not going to happen. If you recall, my 2 steps for solving these equations, step 1 was simplify your equation till there's just a single trig function on one side of the equal sign. Now, on the left side, I've got 3 trig functions. 4 of them, if I consider sine squared, that's actually sine times a second sine, right? So I've got a ton of trig functions on the left. Luckily, I can simplify that left side. I can combine or replace or substitute some of those trig functions by using our trig identities that we've been working on all week long. And so if you ever have more than one trig function in an equation, you need to think about these trig identities first. How can I combine or condense them to make it a single trig function instead? So I want to combine, simplify, somehow make them a single trig function. All right, so what do? Remember that one of my first recommendations earlier this week in our earlier lessons on identities was try writing everything in terms of sine and cosine. Let's try that just to see what happens. First off, sine squared. That's already in terms of sine, so I don't need to change that. I'm going to leave that as a sine squared. Next up, take a look at your trig identities. Where are they in your notes? Flip to that page in your notebook. Find those trig identities where I had you box them up and write them down. How do we write cotangent in terms of sine and cosine? Look at your identities. There is one that says cotangent equals, and it's something with a sine and a cosine. So take a look right now, find it, and write it as that. What is it?
Sine x over cosine.
It's cotangent, though.
Oh. Oh, cosine over sine.
Exactly. That's one of those 2 quotient identities. So I'm going to rewrite cotangent as the cosine divided by the sine. Quotient identities. Right there.
Okay.
Cotangent. Mm-hmm. So with tangent and cotangent, they have 2 different identities that I can replace them with. I can take the reciprocal of it, like cotangent is 1 over tangent, but that won't help me because it still isn't a sine or a cosine. So that's when I look at those 2 quotient identities. And last, cosecant. Let's write that in terms of sine and cosine. And do you remember what cosecant's the reciprocal of? Yeah, you switch that first letter that was a C. Its reciprocal is going to start with an S. So that's 1 over sine. And all this is still equal to negative root 2 over 2. I didn't change anything. I didn't do any calculations. I just apply these identities. I replace something with something that it's equivalent to. Now, how does that help us? I've added more trig functions here on the left, but check it out. This is going to simplify kind of nicely. Since these are all fractions, technically that's over 1, I can think of this as one giant fraction, and I can cancel anything in the numerator with anything in the denominator if they're the same. Well, what do I have in the numerator and in the denominator that could cancel out? Sine squared just means sine times another sine. In the denominator, I also have a sine times another sine. So the sine squared cancels out with the sine times sine. 2 sines up top cancel out with 2 sines in the bottom. What's the only trig function I'm left with now? Simply a cosine. So this big evil expression at the top is simply the same as the cosine of x equals negative root 2 over 2. Cosine to the x coordinate. So look at your unit circle, everybody. Where do you have an x coordinate of negative root 2 over 2? Find it real quick. Don't shout it out yet. Cosine equals negative root 2 over 2. Oh, that's really nice. I want to go snowboarding down there. Yes. So cosine, that's just your x coordinate. Negative root 2 over 2. All right, so that's the left, going to the left on my unit circle, that's quadrants 2 and 3. So I'm looking over here. Cosine x coordinate, up negative root 2 over 2, negative root 2 over 2. So what we got? 135 and 225. Anybody else get those? Yeah? Oh, wonderful, wonderful work. So x equals 135 degrees and 225 degrees. Once you try one of those on your own, and then that's going to be it for the lesson. Then it's just practice time. Tangent times cotangent divided by cosecant equals negative 1/2. So go ahead and jot that down first. Just write it just like it is. And what we want to do is apply those trig identities from earlier in the week. How can I cancel some of that out? And somehow those can combine to become a single trig function. Let's see what you remember from our last 2 lessons this week. Nice. You got this. Don't look, you got it. You know it. Ah, all right. Do you have your identities written down in your notes somewhere? Yeah. Yeah. That is what I was hoping some students might recognize. Any trig function times its own reciprocal will always cancel out. Okay. Yep. Yes. So from this line, you got this equal to that. This is one of our main trig functions. No need to flip anything. Okay. So is this your x coordinate or your y coordinate? Y. So where is there a y coordinate of that number? Cool? Yep. What? Yes. Yes. Is this x or y? Yeah.
Yeah, I realize my unit circle is not right.
Oh no, that's gonna mess everything up.
Yeah.
That's awkward. Do you have another one somewhere maybe?
Yeah.
That might be right or more correct. Something. Oh, dude. So I've seen some students with that numerator rewrite it as like sine over cosine for tangent, and writing cotangent as cosine over sine. And this is all over cosecant. That's fine, right? It's going to work, no problem. Sines cancel out. Cosines cancel out. You're left with 1 over cosecant. 1 over cosecant is just the sine. But if you want to save some time, you might recognize that, hey, tangent and cotangent are, by definition, reciprocals. Anytime you multiply anything, a number, a fraction, a variable, a matrix, by its reciprocal, it cancels out. So a trig function times its own reciprocal just cancels out, just like we saw it over here. Because another way you could write that would be, if I left tangent as tangent, and I rewrote cotangent is 1 over tangent, take a look. Same thing, right? That's tangent times cotangent, cancels out. Any trig function times its reciprocal cancels. So sine of negative 1/2, checking out our unit circle. Sine, that's the y coordinate. So I'm looking at the bottom. Negative 1/2 for a y coordinate. I see one there, one there. So we're going with, I'd say 210 degrees and 330 degrees. Anybody else? 210 and 330? Yeah. Oh my gosh, yes. Or 7 pi over 6 and 11 pi over 6. Oh, that's fantastic. Very good work, everybody. Well, we got like half an hour left. No, even better. Practice time. Online, you will find my practice worksheet on our calendar. If you want to pull that up for those of you at home.